In this video, we are going to discuss electric flux. Now, flux in general is defined as the amount of something that goes through a particular area. So, in this case, it would be the amount of electric field strength, or you can think of it in terms of the electric field vector. The easiest way I can tell you guys to visualize this, since unlike water, so you can easily observe water flowing through a certain cross-sectional area of a stream. In fact, that's something people actually go out in time to check on the health of a stream. Here you can think about the number of field lines going through a specific area. So electric field lines, remember, are supposed to be closer together when the field is stronger and further apart when the field is weaker. So you can count up the number of electric field lines. And we're going to find out that electric flux is going to be affected by the size of the electric field, so the electric field strength, the orientation of the field, and the area that the field goes through. So the bigger the area, if you don't proportionally increase the amount of electric field strength, you're going to get a smaller flux. So we're going to discuss that in equation form on the next slide, but I want to briefly go through the concept of when can electric flux be zero. Now mind you, right now I'm talking about closed surfaces. When I move to the next slide, I'm going to be talking about just the single side of a box versus the flux going through the entire surface area of the box. So you have to be very careful the difference between a closed surface and the flux going through a sheet. So there are three ways that you could have electric flux be zero. The first is that you simply have no electric field, so there's no charge in the box to create an electric field, so therefore there's no electric field strength, so your flux is zero, because 0 times anything is still 0. The second way is to have an equal amount of positive and negative charge in the box. So we're going to define flux as being positive when it goes into the box and negative when it goes out of the box, which means that our positive charge here is going to generate negative electric flux, and our negative charge here is going to cause positive flux, because remember, electric field lines go out of positive charges and into negative charges. So if you have an equal number of negative to an equal number of positive, then you get 0. So if these charges are of equal strength, opposite sign, you're going to have 0 flux, because you have just as much flux going in as you do going out. So you get a net effect of 0. The third way is to have the charge causing the electric field to be outside of the box, but still near enough to the box that the flux actually goes through. So in this case, you would have flux going in and flux coming out, and you're still getting that concept of one of those is going to be positive, one of them is going to be negative, and then they cancel each other out. So the net flux is 0. So these are the three circumstances in which you can have 0 flux. Once again, keep in mind this is through the entire closed surface. So we're relying on the fact that you're looking at both this surface and this surface. If I asked you specifically about this surface, then you can't actually calculate the flux. Is it until I ask you for the net flux of the entire enclosed surface that you can incorporate both this side in 0 flux? So it's very important to be careful of wordings in problems. Alright, so the way that we're going to calculate the electric flux is to take the electric field strength, which is a vector, and take the dot product of it with the area vector. And this is the part where I make everybody's head hurts, because how can area be a vector? So when we say area is a vector, we're defining a unit vector n which acts normal to the surface. So this white line here is our surface. This red dotted line I've drawn here is the n hat vector, unit vector. So the direction of the area is perpendicular to itself. So since we're taking a dot product here, remember dot product is the magnitude of the first vector times the magnitude of the second vector that actually points parallel to the first vector. And to make things a little bit easier visually, I'm actually going to switch these dot products, still do follow the commutative property, so I can do A dot E rather than E dot A. So we're actually going to split the electric field vector into components, or we're going to find the portion of the electric field vector that points perpendicular to the surface, so along the same direction as n hat. So I define angle phi, and here is the angle between the electric field vector and normal to the surface. So this is where we get the second iteration here, where we're going to take the electric field strength times the area times the cosine of phi, where phi is that angle between the electric field and normal to the surface. Now this set of equations assumes a uniform field, so that the electric field is the same the whole way across the area. If we have a non-uniform field, that means that we need to take the integral, so you'd have to have a function of the electric field that is in terms of A so that you can actually integrate. And this would occur for non-uniform fields. And we'll discuss throughout this chapter how we're going to handle uniform fields versus non-uniform fields in a slightly more direct way. And the units for electric flux are going to be Newton meter squared per coulombs. It's very important in this course to start keeping track of units. In Physics 1, everything broke down into a kilogram meter and a second. Here, we're going to see the same style of base units, but it just never seems to be quite as straightforward as saying a Newton is a kilogram meter per second squared versus a joule, which is a kilogram meter squared per second squared. So it's going to be very important to keep track of your units in this particular course.